Hey everyone. This week we're going to be playing with the piezoelectric element of our kit. It's a little piezo buzzer. Piezoelectric element is a piece of material that changes shape when we apply an electric current to it, and that changing diaphragm essentially will create a sound based on the frequency that we assign to it. Our simple circuit here is the simple circuit we'll be doing for all of the piezo experiments. We have a 100K resistor going to ground, any of the grounds on the board, and a jumper wire coming from pin 8 to the positive side of the piezo buzzer. So you'll have a little sticker on there. It looks a little bit like this, and it marks the positive side. It's also marked on the buzzer. So make sure that positive leg is what's connecting back to the number 8 pin on the board. And the code plays a little melody once on startup, so it exists only in the setup part of the code. There is no loop. And if we want to hear it again, we can press the reset button on the Arduino, which will start it up again and play it once. I'm going to power this from a small little battery pack that I got that charges cell phones. It has a little USB connector. We could plug that right in and we'll hear our little ditty. And it plays on startup, and if we want to hear it again, just the reset button. Press it down all the way. So this is the circuit we'll be working with. You can power it from the computer wherever you want. And let's dive right into that code. So this is our first tone demonstration piece of code. We're specifying that the piezo is connected to pin 8 up at the top, and thus far that's our only variable. That's the only thing we need to declare. And the setup is what contains all the notes. The loop has no information. The tone function is the function we're going to be focusing on. In this case, I'm using it with 2 arguments, which pin and what frequency to play. It could also take a 3rd argument of how long to play that note, but that also conflicts with the delay function. They use the same timer, and so if you want to have off notes playing at the same time or immediately sequential to it, I prefer to use 2 arguments with a delay function for the tone. So using the delay here, that will tell the tone to play for 280 milliseconds. The next small section is a no-tone function. A no-tone function stops the playing of a note. It'll keep playing as long as that delay is telling it to, but it'll just keep going and keep going, note to note, without any syncopation of the beats, unless you put in a no-tone function. So the no-tone function takes 1 argument, which pin, and I'm telling it to delay for 80 milliseconds. So we can play with these numbers to tell it how long to be on, how long to play the note, how long to not play a note. The Arduino can only use 1 pin at a time for the tone function, so no matter how many of these tone functions you have, you can never have them all playing simultaneously. So having tone and then no tone and then tone and then no tone, even if you have multiple piezo buzzers, you're only going to be able to play 1 note at a time, not a chord, with the Arduino. So going through this, we just have a series of them, each one having different values for pitches, each one having different values for delays, depending upon how you want to compose your little ditty. At the bottom, I've included in a big long comment various frequencies for notes going up the staff. We have a number of registers here for you to choose from. Just cut and paste those numbers into your tone functions, and you can hear what that tone sounds like. And here's the next piece of code. It plays a very similar melody in a very different way. Let's take a listen. Similar melody, but it's accomplished in a much shorter piece of code. And we're doing that in a couple different ways. The first thing is including a library called pitches H, which essentially defines all of our notes for us, sort of like I did for you in the first one. But now, instead of having to manually cut and paste each one, we can use these names, E5, C4, G5. 0 is no tone. 0 is basically a beat in this particular instance, and now we're using what's called an array. These two square brackets put together is indicating an array, and an array exists between two curly brackets, and it includes a number of either variables or numbers separated by commas. So as long as each one of these has a comma in between them, the array considers them a different place in the array. And this array is something we can count through, with a for loop. We have a second array called note durations, and this is going to determine how long each one of these notes in this melody play for. And you'll see down below we'll be using quarter notes, fifth notes, thirds. Manipulating these numbers manipulates how long the note plays for based upon what's down here in the setup. So again, this happens just in the setup, inside of the setup curly brackets, and it is itself a for loop. This for loop uses a variable called this note. Now this note we haven't declared anywhere, and in a for loop we don't have to declare it anywhere but inside the for loop. So we're telling it, for the integer this note, which is equaling 0, this note is less than the number 8 in value, add 1 to that variable. So no matter what number it is, as long as it's under 8, it's going to keep adding 1 and then iterating through this loop. The reason that it's 8 is because our melody contains 8 notes. If it were 10 notes, that would be 10. If there were 12 notes, that would be 12. So if you want to use this configuration to construct your own melodies, you can start to change that to change the duration of it. Now this is where it gets a little bit more complicated. I've tried to notate a little bit. This is also a modified piece of code that you can find in the example sketches. So we have another integer, note duration, that we're assigning the value of 1000 here. And the reason we're doing that is because 1000, as we use it, will be 1 full second. And we're now going to be dividing that by a number from the array note durations up at the top here. So note durations array, and if we're going to tell which position in that array by the variable this note. So in the first time through, this note is 0, so that means this note can be replaced by the number 0 the first time through. And in an array, the first position is actually designated by a 0. So that is a 5 the first time through this for loop. So the note duration is going to be 1000 divided by 5. The tone will be played, determined by this position in the melody array, which pin, which note, and the note duration. So this is the 3-argument way to make a tone play. And that note duration, that variable, is determined right here by the array that we've set up above for the note durations and the steps it's taken through its for loop. To keep this from being one constant tone, we have to have a pause in between notes here. So we're declaring another just local variable, an integer, pause between notes, and that's equal to essentially a little bit longer than the duration that the note plays. So we're also using note duration, the variable, which we've determined up here, times 1.35, that's about 35% longer, and that will make a pause between note delay. So that number is determined right above it, and that delay will stop the tone function and give you a space in between your notes. So very simple, every time it goes through it increases this note by 1, this note changes the position of the arrays above it to determine what note and for how long it's being played. You can listen to it one more time. And here's the circuit setup for the third piece of code. We're going to still be using the piezoelectric element as well as a 1 mega ohm resistor. So we have the piezo and the 1 mega ohm resistor connected to each other in parallel. It's kind of hard to see on the board. The positive leg of the piezoelectric buzzer is connected to one leg of the 1 mega ohm resistor, and that positive end is connected back to ground. The other side, technically the negative side of the piezo, is connected to the other leg of the 1 mega ohm resistor, and then back to the analog 0 port. And we're going to be reading information from this to turn on and off a little onboard LED. Let's see if we can give it a knock and turn it off. Takes a little bit of a whack. So the circuit again has the piezoelectric element hooked up in parallel to the 1 mega ohm resistor, meaning both of their leads are connected together, each in the same row. The positive side of the piezo goes back to ground, the other side goes back to analog 0 for this circuit. Let's see what the code looks like. So here's the code for the knock sensor. We have some variables at the top. Our threshold, which is the number that we need to surpass to change the state of the LED. The declaration of analog 0 as the sensor pin, and pin 13 as our LED pin. That's the onboard LED that was turning on and off in the demo previous here. If we hook up a regular LED to that, that too will turn on and off, but we don't have to. There's a built-in one that lets us do this kind of thing for testing. These variables, sensor reading, is what's going to store the information from the knock sensor. And this variable, LED state, this is a different type of variable than we've used before. It's a state holding variable, so it's not a number, it's a state. This is starting at low, meaning 0 volts or ground, and it toggles between low and high, high being the opposite of low, low being the opposite of high. That will become more clear in a sec. In the setup, we're declaring the LED pin as an output, the knock sensor as an input, and starting serial communications, we can look at the information that's coming from the board. In our loop, we have a sensor reading. We're declaring our sensor reading here as something that's analog reading the knock sensor. So as it goes through the loop, it's going to keep listening to that knock sensor and store what it reads into the sensor reading variable, and then we're going to print that out to the serial monitor. And we have an if condition here. If the sensor reading is greater than or equal to the threshold, then we're going to change the LED state. This is a different sort of functionality than we've dealt with before. This putting an exclamation point in front of a variable like this means opposite. It means not, it means the other. If there's a two-choice sort of situation, that being high or low, on or off, up or down. So if the LED state is high, then make it low. If it's low, then make it high. So with one statement, we can invert any information coming in to whatever the opposite is. So that's why it was a low declaration up at the top for our LED state, because we wanted to start off. And then every time our sensor reading passes the threshold, it'll turn on, and it needs to pass that threshold again to turn off again. And that is being written here. In the digital write command, the LED state, again, is either high or low. So the LED pin will be written high, 5 volts, or written low, 0 volts. That ends the loop. We have a small delay so that the serial buffer doesn't overflow and give us some problems later on. We can look at it through the monitor itself with the little inspector icon and look at the numbers, which is okay. If we hit the knock, we can start to see some digits flow by. This will give you a sense of what you want your threshold to be. But I find a more fun way to do this is to go up to Tools, use the serial plotter, which will plot these numbers on a graph. So right now we're at 0. As we start to tap, it'll scale the graph for us. So that last one was just under 120. We can see the knocks visually, which I find much more fun, much more fascinating, interesting to compare over time, see them a little bit longer. So using this information through the serial plotter and the serial monitor, you can adjust your threshold to suit.
Okay, so here's the next circuit. It's the same setup for the piezoelectric element as we had in the last section. Now we just have 3 LEDs hooked up to pins 11, 12, and 13. So I tried to color code the wires. The green one goes to pin 11, yellow to 12, red to 13. They all have 220 ohm resistors on their negative side, back to ground with this jumper wire. Okay? So this circuit, what this is letting us do is count. Simply count with knocks and lights. So we hit the first one time, second time, third time, fourth. Simple operation, but let's take a look at the code.
So here's the code for our second piezoelectric circuit that counts our knocking. Our constant integers are at the top, our pin assignments. We've added 2 arrays for our pin numbers and the states of those pins. There's 3 LEDs, but I've included a 4th number in both arrays. It's sort of a dummy position that lets us do some math that wouldn't work with just 3. And we've got our initial state assignments for the LEDs and a new integer called count. That's what's going to let us do our counting and keep track of how many times we've heard knock. In the setup, we're declaring our inputs and outputs and our serial communication back to the computer so we can look at information if we need to. And in the loop, we start by assigning sensor reading the value of what the knock sensor reads. So it's an analog read, and that's where we're going to pin A0. And that's going to be the function that says, hey, is there a knock? We're going to print some information out so we can analyze it if there's any troubles. And then we have an if statement. So if the sensor reading is greater than the threshold, so if we hear a knock, we're taking the variable count and we're adding 1 to it. We're going to say if count is greater than or equal to 4, it goes back to 0, and we're going to write the last pin in the array there, the red one, back down to low. This is kind of what takes care of passing 3, since we only have really 3 elements we're working with. So if it's not above or equal to whatever number count is in the pin array, the opposite of whatever the state is in that same position in the state array. While at the same time, we're going to be digitally writing the pin before the one that just turned on, that's count -1, to the state of count. So whatever the position of count is, 1, 2, 3, or 4, in the states array, that's what we're going to write here. So we'll see how that will actually work out in our favor, because that in the states array will always be low, rather than the opposite of state, which will always be high. So this little function takes the counting, translates it into both which number pin and what state that pin is in. The second line essentially turns off the previous one as it turns on the one after. This is also why we need the dummy position, because if we're at 0, count -1 means nothing. So the dummy position in both of our arrays takes care of that. So this is how this guy works. Have fun, try making a bunch of them. Try hooking up as many LEDs as you have and see how high you can count with lights. Or what other things you could control with this knocking mechanism.
So here's the circuit for controlling an RGB LED. So in your kits, you'll have an LED that has a multitude of legs. And these legs each control essentially a separate small LED inside here. One of them is slightly longer than the other ones, and that's going to be your negative leg. All the other ones are positive legs that go to pins on the board. Each one of those has a 220 ohm resistor protecting it, and I've color coded them to the red, green, and blue pins on the LED. So from right to left in this orientation, it's blue, green, red. Now again, this guy here, the longest one, that's your negative, your common negative for all of these tiny LEDs. So let's shove this guy back into the sockets. So each one has their 220 ohm resistor protecting it, except for the negative line, the ground. And these go back to pins 9, 10, and 11. So that's blue for 9, green 10, red 11, and any of the grounds to that middle one. So what this first piece of code is going to do is just cycle through all the colors: red, green, blue, cyan, magenta, CMY, and show you the range that this particular device can create.
So here's the code for the RGB LED, sort of its test pattern code, if you will. The integers declared at the top are real simple, the R, G, and B pins. The setup's real simple, we're just declaring those as outputs, and the loop is pretty simple too. It's giving it a function, and then 3 values. The R, and then it's cycling those at different values between 0 and 255. That's off or completely on. Any number in between is just a variation of that. And delaying that for 1 second so you can see them. The big difference here is that the void loop isn't everything in this piece of code. We have something below that loop. We've never had something outside the loop before. And this is it. It's a new function. It's called void RGB underscore color. So this is a function that's created. This isn't something that lives inside of the computer. This is something we are making on our own outside the loop that can be called up in the loop itself as a function. So this void RGB color has 3 arguments separated by commas. This value called int red light value, int green light value, int blue light value. So those values are then it defines what it does down here. Let's say it says the red light pin analog writes the red light value, analog writing the green light pin the green light value, analog writing the blue light pin the blue light value. So we're doing analog writes out of these pins. That's why it's 9, 10, and 11, because those 3 pins have that tilde next to it, the little squiggly line. That means that they can simulate analog writing. And we can then do more than on and off. We can do this 0 to 255 range with those pins. And this function at the bottom is what lets us define that this is a new function that takes certain pins and does certain things with them. And then lets us call it up in the loop above it. It's pretty simple, and you can start playing with what these values are, see what they look like, see what kind of off-brand, nasty colors you can make with them, how long you can keep them on, and you can even start to think about this in context with the knock counting. If you wanted to try to combine these 2 programs with changing colors by tapping your piezoelectric element, that's also something you can do.
So here's the next circuit for the RGB LED. It's the exact same thing happening on the left side of the breadboard, and all we've done is added a voltage divider onto the right. So we're using a light dependent resistor that's going between the analog 0 at the center, where it connects with a 2K resistor. The right side of that light dependent resistor is going to 5 volts. The other side of the 2K resistor is going back to ground. So we have ground, analog 0, and positive 5 volts. And with the second set of code, we're using the analog read from this light dependent resistor to vary some of the values of R, G, and B so that we can change the color of that with our hands, with light, with whatever, so we can start making it more responsive. And we can go check out the code for this.
And here's the code for the second RGB experiment. We've actually been able to make it much smaller, and we're adding only one variable, or two variables I should say, the light sensor pin and the adjust variable, which will hold the information from the light sensor pin. Same setup, the loop is only slightly different. We're making that declaration that adjust is equal to whatever the analog read of the light sensor is, and we're going to map that to make sure it just stays between 0 and 255. It kind of gets readings between 0 and 300, so we're just going to scale that back to keep within the tolerances of what the light wants to take as an analog write. And then all we do here is tell it that adjust is equal to other things in that RGB declaration. It's the same function that we created before. Now we're just using it a little bit differently. Now that the machine knows what adjust is, we can make R adjust, G 255 minus adjust, and I'm leaving blue out of the equation. If we had another light dependent resistor, we could make that control a third option. If we had three, we could have each one control one of these R, G, and B elements. I've made a much smaller delay so that this happens much more quickly, and you can see that light fade in and out between red and green. If you change the declaration of where the 0 is, if I switch between the center position with this declaration of 255 minus adjust to the right hand side, that will make it fade between blue and red, and vice versa. So have fun playing with this. See if you can use adjust in different ways. It doesn't just have to be adjust and the total minus adjust. You can have adjust divided by 2, adjust divided by 4, subtract it from itself. See what it does, see how it varies.